The encoder is the first element that we find in a digital modulator. In this video, we will see how to design this element to have the best possible performance. And the encoder, this element, after the initial bits to symbols conversion, will transform this sequence of symbols in a sequence of vectors. Vectors representing by symbol intervals the signal that is transmitted through the analog channel. This is the role of the encoder. Now we are going to see how to design this encoder to get the best possible performance. The encoder converts symbols in vectors, vectors that represent signals, the M signals that we have at the modulator. And to design the encoder is equivalent to select the alphabet of these vectors, the constellation. We will have capital M symbols, and this means that we will have M bits per symbol, with M being the logarithm in base 2 of the number of symbols. Now it is convenient here to remember the relationship between the two transmission rates that we have in a digital communication system. The binary rate, the bits per second, and the symbol rate, the number of symbols per second or bauds. And these two rates are related by the product with the number of bits per symbol. Two constraints must be taken into account to select the constellation in the encoder: performance, probability of error or bit error rate, and energy. The performance is related with the distances between symbols, and in fact it is determined by the minimum distance between symbols. And the energy is related with the norm of the vectors in the constellation, because the energy is the square norm. Therefore, we want symbols as close as possible to the origin, with as low as possible norm. And basically, the design of the encoder consists in a trade-off between distance and energy. The idea is to guarantee a minimum distance, to have a minimum performance, with symbols as close as possible to the origin of the coordinates, which have as low a norm as possible. And to minimize the energy for a set of distances, it is important to have a zero mean constellation. A good trade-off can be obtained with the sphere packing technique, which is the optimal design technique for an encoder. Basically, the idea is to guarantee a minimum distance, because the minimum distance will determine a minimum performance. And to do this, symbols will be modeled as a sphere whose center is the symbol and the diameter is the minimum distance. With this model, if we have two spheres in contact, they are at minimum distance. And because of this, the design of the encoder can be stated as follows. We need to place M spheres of diameter, the minimum distance, in the smallest possible space. And to guarantee that with the distances we have the minimum possible energy, it is important to guarantee that the constellation at the end has zero mean. In a one-dimensional space, the solution is very simple. We have spheres in contact, centered at 0, and this means that the coordinates are integer multiples of half of the minimum distance. In fact, odd integer multiples of this half of the minimum distance, plus and minus 1 times this half of the minimum distance, plus and minus 3 times, plus and minus up to the number of symbols minus 1, plus and minus odd integer multiples of half of the minimum distance. In a two-dimensional space, we'll have a central sphere, and then the following spheres will be located in circles around this central sphere. These layout is much more efficient than a rectangle structure like this one. It's possible to see that this produces an hexagonal arrangement, and this hexagonal arrangement is clearly much more compact than a rectangular arrangement. Once that we have placed the spheres with this arrangement, it is important to guarantee a zero mean constellation. And if we have a constellation that initially is not zero mean, to convert this constellation in an equivalent one with zero mean is relatively simple. We need to compute the mean of the constellation, the mean of the coordinates of the symbol for each dimension, and then we can construct the new zero mean constellation just by subtracting to every symbol in the previous constellation this mean. Just as an illustrative example, if we have this constellation, clearly this constellation doesn't have zero mean. The mean in the first component is 1/2, the mean in the second component is 1. If we subtract this mean to every symbol in this constellation, we get this constellation that has zero mean. Analytically, if we have the coordinates of the 4 symbols, we can obtain the mean of these 4 coordinates in both dimensions. Then we subtract to every symbol this mean to obtain the new constellation. The mean energy per symbol of the original constellation is much higher than the mean energy per symbol of the zero mean constellation. Now, if for instance we need a 64 order constellation, initially we will get the hexagonal arrangement for these 64 symbols, we'll compute the mean, we'll subtract it to have a zero mean constellation, and we can see that the mean energy per symbol of this kind of constellation is relatively much lower than the mean energy per symbol, for instance, of a rectangular structure.